So I'll be talking about a damage meso model for laminated composite structures with material non-linearity. So I'm aware of the things or the lectures that have been done previously. Yeah. So this will be little of from what you are doing. First, I will talk about the composite. What is damage meso model? What is damage? I will just introduce that thing, and then I will talk about where do you get the material non-linearity, and in a very simple way, how do you handle this material non-linearity when you are dealing with this damage. So this is the layout of my presentation. So first I will introduce various damage mechanisms in the laminated composites. I will be talking about the unidirectional fiber composite. Then I will talk about a particular damage meso model. I will introduce what is meant by damage, what is meso model, and then I will talk about where do you get this material non-linearity. Then I will just represent some key results and conclusions. Okay, so as you know, these composite materials, they have excellent properties. So specific strain, stiffness, and so on. Okay, so depending on that, you have different applications. One of the important thing, or one of the important property of these materials is that you can tailor any of the property. So that is the biggest advantage or the biggest good thing about the composite. So that is why they find application in various areas. So they are applied, or they find applications in critical components in space industry, marine industry, automobile, civil, and so many other applications. So when you are talking about these critical applications, then you are also talking about the modeling the structural response. So this can be a global response, this can be a micromechanical response, it can be inelastic or the plastic, and damage. So as far as I remember, as far as I recall, that some of the things that have been talked for the global, I think the buckling and that part is done, or it is okay. So I think we will be talking about that, the snapback and other things. Professor Padevi is going to talk about that. I think this part is micromechanical. Are you doing any micromechanical? No, no. Okay, so this part is not there. But I think Professor Pritam Chakravarti is going to do inelastic part and the plasticity part. So I'm going to fill this damage part. Okay. So now, if you are going to model, then you will have in this all this type of this responses. At some place you will have the non-linearity because of the different reasons. Either you may have non-linearity due to the geometry, non-linearity due to the material, or non-linearity due to this plasticity or damage and so on. Okay. So ideally, if you want to do a reliable analysis, certainly you would like to do a 3D elasticity analysis. So in generally, you will see that is very difficult for all the problems to do 3D elasticity analysis. So again, there's one more challenge when you go for the composite material, is that heterogeneity. So this composite material is composed of two or more different materials. So it will lead to the heterogeneity, and other thing is that it is orthotropic in behavior. So unlike your metals, which are generally isotropic, so this is orthotropic in nature. So what is done in case of this composite modeling is that you use reduced models. Okay, so you make some assumptions depending on your structure and the orthotropy, heterogeneity, and so on. Okay, and then you come down from 3D to 2D or 1D line. Okay. So, and once you do that thing, and then you find the approximate solutions by using finite element method. So I will now introduce that the failure mechanisms that are generally seen. Okay, or these are the key failure mechanisms in fibrous laminated composite. So these can be categorized at two levels. It's a micro level failure mechanisms and macro level failure mechanisms. So in micro level failure mechanisms, so these are the failure mechanisms at fiber and the matrix level. So since I'm sure that you are aware of composite materials, I'm talking here about the fiber reinforced polymer composites. So I'm talking about the fibers of carbon and glass. So these are generally in micron sizes. So the diameter of the carbon fiber, it is about 6 to 8 microns. In case of glass fiber, it is 15 to 20 microns and so on. So you are talking about the failure mechanisms at the fiber level. So that is why they are called micro level failure mechanisms. So again, in that you can categorize them as fiber level mechanisms, matrix level mechanisms, and the mechanisms which are coupled. So the failure in fiber will lead to failure in matrix, or failure in matrix will lead to failure in fiber. So these are, then again we have one more type, that is the fiber matrix coupled mechanisms. Then we have macro level failure mechanisms. So generally if you see these things, these are happening in a ply, or it is happening in a single lamina. Okay? So these are also called as intralaminar failure mechanisms. So whereas this one, this is happening at the macro level, or it is happening at the level of structure. So one of them is delamination, and the other one is longitudinal splitting, or is a coupled, I will say, macro mechanism. So I will show those pictures. So again, as I said, intralaminar damage mechanism. So what are the possible things? So one is that you can have the breakage of fibers. So this picture shows that, okay, this the cylinders are nothing but these are the fibers, and you can see that these are broken fibers. Then you have fiber matrix interface debonding or diffuse damage. So this is the micrograph which shows these are the fibers. Okay, so these circles are the fibers. Okay, and this is a material, matrix material. So the bond between fiber and the matrix becomes weak, and there is a failure. Okay, so this is called as diffuse damage. Then another form of the damage or the failure is the transverse matrix cracking. So what happens is that there is a crack in the ply. So this is a laminate, so it has different plies together. So what you see here is that in this ply, okay, so this is the ply in which the fibers are going into this screen. So you can see here that there is a crack which is going through the thickness of the ply. Similarly here there is a crack which is going in the thickness of the ply. Similarly here. Okay. So these are the pictures which symbolically show the fiber breakage. So these black lines these are nothing but these are the fibers, and the remaining part is the matrix. So what you see is that there can be a fiber breakage, okay, at one place, and then it can happen in subsequent places. This is one of the ideal case I'm talking about here, I'm showing here. In practice it may not happen like this, but what happens is that one fiber fails, in the neighborhood of that, okay, so there is a stress distribution and the neighbor fibers fail. So this is what it represents. Okay, so this is fiber breakage. So this happens when the longitudinal strength of the fiber is exceeded. Okay, at that time it fails. This is one of the reason. Then another is that fiber kinking. So as I said, these fibers are very thin. So this is just 8 microns or 20 microns in that. So and they come in a bundle. Okay, so you will have a bundle of 6,000 fibers, 12,000 fibers, 18,000 fibers or so. You cannot have the same individual fibers. So it comes in a bundle. So because of handling or some other reason, it is possible that it may have some kinks at some places. Okay, so this is called fiber kinking. Another mode of failure is that the fiber bending. So these are long fibers. So when you are putting them in the matrix material, or when you are making the composite material, it is possible that you are not stretching them sufficiently, and so when they are set, or when they are cured along with the matrix material. So, it is possible that there is a bending in the fiber. So, this is one more level of fiber failure, is that fiber splitting and radial crack. Maybe I can go to the previous picture. So, as I can see here, this is the fiber, this is split along this radial directions. Okay. So, as you can see here, it is split. Okay. Here it is split in two halves, whereas it is you see that there are radial cracks develop into this. Then another level of failure is that this matrix between the adjacent fibers that can develop cracks. So, there are two types of cracks. Okay. One in which these cracks, okay, these are developed perpendicular to the fiber length. In the other one, they are developed along the fiber length. So, depending on the loading and the properties or the strength of the matrix material, either of this is possible or both of them is also possible. Then another type of failure is this matrix interface cracking. So, what happens is that at some places, let us say there is not a proper bonding between fiber and the matrix. So, what will happen is that this interface between this fiber and the neighboring matrix is weakened and it develops a crack. Then this is fiber matrix coupled failure mechanism. So, in the previous picture I showed that this fiber breaks and there is a redistribution of the stress and neighboring fibers also fail. So, in this case, this is a slightly different case. What happens is that, let us say the fiber has failed in one region, then what happens is that the stress distribution takes place and in the neighboring region, the bond between fiber and the matrix becomes weak and the fiber is pulled outside. Okay. So, earlier it was supposed to break here, but what is happening is that it is broken here and then it is pulled. Okay. So, this is called as fiber pull out. Then this one, it can lead to the interfacial debonding, is that the fiber has broken here. Now, what happens is that the stress distribution takes place and the bond between fiber and the matrix near to this break, okay, becomes weak and there is a interfacial debonding. Sometimes what happens is that because of this interfacial debonding, the crack will propagate inside and instead of going further, it may go in the thickness direction. Okay. So, this is called transverse matrix cracking. Another possibility is that, so let us say now the fiber has broken here, then what will happen is that the stress distribution is so high that it will catastrophically break the neighboring fibers in this. Okay. Or else it may happen that if the matrix material is strong, then it will propagate and it will stop at the next fiber. So, this kind of the coupled fiber failure mechanisms are there. Then at the macro level, so this happens at the structural level when you have two plies joined together, then what happens is that there is a separation between these two plies. So, this can be internal, this can be at the edges, or this can be at anywhere, okay, depending on the loading situation as well as depending on the structural detail levels. So, this is the separation is called delamination. I have the same picture again in the next slide, I will explain that. Okay. And as I said in the previous slide is that the ply can split along the fiber. Okay. So, the crack that has developed between the matrix material, it goes along the fiber length through the thickness of the ply and the entire ply is separated. So, this is called as longitudinal splitting. So, this is the delamination. So, as I said earlier, so there are many layers and what you see here. Okay, so, this is the interface between this ply and the next ply. So, this black region is nothing but these plies have been separated. Okay, they have delaminated and they have come apart. So the crack or the surface or the bonding between these two plies has become weak due to the loading or some reason, and then it is separated. Okay? And this one is what it shows is that this is interaction between intra and interlaminar damage mechanisms. So there was a delamination, it was propagating like this, then it sees that okay, now it cannot propagate along this interface. So what has happened is that it has found that there is a weak direction in the ply itself. So what has happened is that the crack, which was the interfacial crack or the delamination that was growing along this, so that has moved in the thickness direction. Okay? And it goes in the next interface. Then again it sees that the next interface or the interface below this, okay, is weak. So again it has propagated like this. And also here you can see, okay, so when it was separated, it has seen that okay, there is some scope that there was a weakness in the ply, so it has led to the crack. So these mechanisms are coupled. So this matrix transverse cracking can lead to the delamination, or the delamination can lead to matrix transverse cracking. So these are the coupled mechanisms. Okay, so with this introduction to the various damage mechanisms, so now let us see how do you take care of this failure. So these failures are the macro level. So how do you take care of this failure, okay, or how do you characterize and how it is taken care into your material behavior. So this is the very I will say popular picture. So what you have is that let us say you have a continuum body, and then let us say these dots are nothing but these are the voids or cracks. Okay, then you take any section, okay, the normal is shown here. Then let us say you have taken some area, and I am showing it here. Then what you have is that you have the intact area, okay, or the total area is S, and then you have these dots which is damaged area, and let us say you have some portion of it. So whatever load that is taken or resisted by this surface normal to this will be this total area minus this damaged area. So this area, okay, so this is the area, this is the effective area we are calling it. So this effective area will take the load, and that stress is called as effective stress. So this is your actual load and this is the effective area. So what you do is you make some adjustment, that is you take out S common, then what will happen here is that this will be represented as, this S bar is represented as S times 1 minus SD by S. So this SD is nothing but your damaged area upon total area. So this ratio is defined in this case as damage, so damage indicator. So this will go maximum 1. So when SD becomes yes, then it becomes 1, and when SD is 0, so Dn is 0. So that means your damage parameter will vary between 0 to 1. So 0 means there is no failure, and 1 means it's a complete failure. Okay? So this is how is your effective stress has been represented. Okay? So if I further work with the stress strain relation, okay, then I can also define the effective strain. So if I do that thing and I replace this effective stress by this, then what I see here is that you have the nominal stress divided by this term. So what I see here is that this E times 1 minus dn. So E is your original stiffness. So now what has happened, because of the damage, now it has been reduced by this factor 1 minus dn. So the effect of this damage can be characterized in the material through the reduction of the stiffness. Okay? So this is just one simple example where the concept of this damage variable, okay, effective stress, effective strain, okay, has been introduced, and how do you take care of this damage through the reduction of stiffness. Okay. So, this is the source which will give the non-linearity, because as your load is changing, these things are changing, your stiffness is changing. Okay. Okay. So, here what the model that we have taken is the damage meso model. So, as we said, the actual structure will be like this. So, you have different layers joined together. So, you have a perfect bonding between the two adjacent layers. Okay. So, I may go back, yeah, and again what you see here, you can clearly see in this picture is that this laminate is nothing but is the alternate stacking of this ply, and then you clearly see an interface between this ply and this ply. Similarly, you can see a interface between this ply and this ply. Yes. So, likewise here also. So, the first assumption that is made is the mesoscale. So, it means that you are breaking or you are assuming this laminate as alternate stacking of layer and interface. So, layer means you have the matrix and the fiber, and in the interface it is pure matrix material. So, it is a very thin layer which is made up of matrix material. Okay. So, you are talking about at these scales. So, this is the ply which is of thickness 0.15 or 0.125 millimeter. So, that is about 125 microns. Okay. So, this is the scale you are talking about. This is neither the micro or this is not the macro. So, this is in between that. So, that is why it is called as mesoscale. So, you are talking or you are characterizing the failure in individual ply and individual interface, and these two things will combine alternately to form the laminate. Okay. So, this is the first assumption. The second one is the internal variable approach. So, it relates the effect of damage to mechanical behavior. So, this is the same thing as I said, it relates the effect of damage to the mechanical behavior. So, your E gives the stiffness, that is the mechanical behavior. So, your Dn is called internal variable. Okay. So, then the method of local states. So, it relates the damage to the thermodynamic forces associated with the strain energy. Okay. So, this is the like dual of the this thermodynamic force is nothing but is the dual of this damage indicator. Okay. So, when you have this damage indicator and thermodynamic force together, so it will give you back the energy or strain energy or the free energy. Okay. So, with this now we will do step by step that how these different mechanisms or failure mechanisms affect your stiffness. So, in doing so in this development, what is done is that only key or the important failure mechanisms have been considered. The first one is the fiber failure. So, as you know, in the composite, fiber is the main load carrying constituent. So, majority of the load, okay, when it is applying along the fiber direction is carried by the fibers. Okay. So, if the fiber breaks because it has more stiffness as compared to the matrix material, the stiffness of the lamina decreases drastically. Okay. So, this is one of the important failure mechanism. So, one more assumption is that when you are considering the fiber failure, so it will affect only the modulus in the fiber direction. Its effect on the failure on the other direction is lesser. Okay. So, if you see that the fiber is broken this, then it is almost catastrophic failure. So, there is no chance that you will have some failure in the other direction and then this will fail. Okay. So, it is the assumption that if the fiber is going to fail, it is going to affect only the failure, or it is going to affect the stiffness in fiber direction, that is direction E1. Okay. So as we said, this material is orthotropic. So you will have E1, E2 and E3. E2 and E3 are same because this material is transversely isotropic. Okay. That means the behavior in 2 and 3 directions are same, but in one direction it is different. Okay. So this is the strain energy of the damaged fiber is given like this. So it is affecting only the Young's modulus in the length direction of the fiber. It is not affecting any other depth. Okay. And then if this is your strain energy, then you can define the thermodynamic force in this way. Okay. So where dF is the damage indicator for fiber failure. So how do you evolve the damage? So you are talking about now when it is going to happen, and when it is happening, that how will propagate. Okay. So you are talking about the initiation to its last stage. So in this case for the fiber, so you are talking about this thermodynamic force. So if this thermodynamic force, whatever you got here, if it is less than the thermodynamic force in tension and compression, these are the critical one, this YFT and YFC, these are the critical, that is the corresponding to the maximum strength of the fiber in tension and compression. I can do a similar thing here for maximum stress in the fiber and the fiber for tension and compression. So that is basically you are talking about the fiber strength in tension and compression. Okay. So this, then if the stress in the fiber, okay, 1, that is along the fiber, if the stress is tensile, then I will compare what is the tensile thermodynamic force, critical thermodynamic force for the fiber. Then if it is more, then I will have this damage indicator as 1. Why I am putting 1? Because for carbon fibers and the glass fiber, the failure is brittle. So either it will go on stretching and then ultimate failure. There is no failure which is increasing, okay, step by step. It is either intact or it is complete failure. So that is why either you will have 0 or 1, both in tension and compression. So now for the case of the fiber matrix debonding, so there are different things happening. So you have the bonding between this fiber and the matrix. So if it is weakened, yes, if it is weakened, then what is going to happen? In this direction, the strength is reduced, yes. In the shear also, it will be reduced in this direction as well as in this direction, yes. So because of this, you have the effect of these damage indicators. So 2, 2 means in the normal direction to the fiber, then 1, 2 and 2, 3 are the shear effects. So your damage in the interface is going to affect your E2 modulus, and then also it is going to affect the shear moduli. Okay. So again, there is one more assumption is that this damage is considered to be transversely isotropic. So whatever you have in this direction is also in the same direction, means in the plane direction as well as in the thickness direction. Okay. So if I am considering only the fiber matrix debonding, and if I consider all these effects, okay, then the strain energy that I get is this, and for these damage parameters I can have the associated thermodynamic forces which are defined like this. So this is the next mechanism, which is, as I said, the transverse cracking. So there are two possibilities. These are the cylinders are nothing but these fibers. So the crack can be longitudinal or crack can be perpendicular to these fibers. Okay. So when you are having the crack, and if I am looking at this volume, and if I look at the stiffness that I have, so what you get is that there is not a complete reduction in the stiffness. So you will have still some stiffness. So that is why we have put these parameters. So these parameters are nothing again between 0 to 1. So there are two types of cracks, as we said here, is a longitudinal crack and the transverse crack. So these cracks develop easily, whereas these cracks do not develop easily, because when you are applying the load in the fiber direction, most of the load is taken care by fiber. Okay? So the fiber fails first in this case, and then the matrix, so there is very little chance to develop this kind of cracks. So whereas in this case, if you are applying the load perpendicular to the fiber, it is very easy to develop these cracks. So this is the prominent matrix cracking phenomenon is seen in the unidirectional fiber composite. So but still this also happens, and its effect is less than 5% on the material degradation, and sometimes it goes undetected. Okay, so when you are looking, or when you are looking or characterizing, or when you are doing the NDT or so, you should be very careful to quantify these numbers. Okay, so if I consider that matrix cracking or so, then what is going to happen? Sorry, I will go back. So this one, so it is going to affect your strength or the stiffness, stiffness in this direction, longitudinal the fiber direction, and then in the shear directions. So my stiffness in the longitudinal direction, perpendicular direction to the fiber in this plane, and in the shear is going to affect. So these parameters are, now you see that it is affecting your stiffness in two direction and the shear. So for this strain energy, now you can again define, or you can get this associated thermodynamic forces for these damage variables. So what we did is that we consider these different mechanisms together now. So individually, first we talked about the fiber failure, then how it is going to affect the stiffness matrix, then we talked about the fiber matrix debonding, and then we talked about this matrix cracking. Okay, so when we put all these things together, so this is what I will have in my stiffness matrix. So now what is left? Now the failure at the macro level. So that is the delamination. So in the delamination, the initiation in this case is given in terms of 1 Mises stress criteria, because the matrix material is assumed to be, or it is isotropic in nature. So I can apply 1 Mises stress criteria. But for the propagation also, again what we are doing is we are defining the strain energy of the damaged interface. So again in this case, you will have the damage propagation for the delamination in 3 modes. Yes, so mode 1, then mode 2, and mode 3, sliding mode, okay, opening mode, and so you have 3 different modes. So for each of the mode, now you have different indicator. So in case of the opening mode, so the crack will propagate, it is assumed that the crack will propagate, or the delamination will propagate only when the stress is tensile. If it is compressive, then there is no damage developed into that. So this is the strain energy of the damaged interface. So corresponding to each damage indicator, again now you can define the thermodynamic force. What is it? Yeah, you can do that thing, okay, but 1 Mises is like you are considering all the things together, okay, it's energy based criteria. So you have all the things together. Okay, so you can also do that thing for that. So yeah. So here also you can do that thing. If you want, you can check the individual one and then you can do that. Okay, but whereas for the initiation, so that is more appropriate in case of isotropic material. So that is why one Mises criteria. Okay, so for the propagation, what is done is now you are talking about 3 modes. Okay, so I cannot I don't want to do individual mode one by one. So what is done is that you define equivalent thermodynamic forces when you are having where you are having all the 3 modes. Okay, and what is done is that you basically this thermodynamic force is nothing but you are trying to capture the mixed mode failure. Okay, so this whatever it is written, it is just modified form of the mixed mode fracture. Okay, of the delamination. So depending on that, you will have this lambda 1, lambda 2, alpha, and these parameters. So you will get depending on what is the strain energy that you get when you are mixed mode failure. So you do a parameter fitting and then you can get these material parameters. So one more thing again it is defined here is that the crack will propagate only when the thermodynamic force, okay, in the next step is only when greater than the whatever thermodynamic force that you have in the previous step. So sorry. So based on the behavior of the matrix material, whether it is a brittle material or whether it is a ductile material also, and you can do slightly one more fitting based on the indicator N. So you can get the corresponding damage indicators. So in this case, instead of having separate indicator for each of the mode, what is done is only one indicator has been used. So that it means that the failure in 3 modes will happen simultaneously in or together. Okay. So one more thing in this damage is that, so if I look at the delamination part, is that in the opening mode, so the delamination will propagate only when the stress is tensile in nature. Okay, the same thing is assumed for other modes, is that when you have the state of stress locally tensile, then only the possibility of damage growth. If the locally the state of stress is compressive, then whatever the damage is there was there earlier, it stays that. That means we are considering the damage is dormant. Okay, the material may be damaged. Okay, so whatever damage is there, it will stay as it is. Okay, and another thing is that there is no healing in the compression. Okay, so when the material is compressed, it is, we may assume that there is a healing of the material, but we are not considering that. What we are considering is that when the locally the state of stress is compressive, then the damage stays dormant. Okay, so whatever damage state was there earlier, it remains that. So with this, now we will see how it has been implemented. So you have this input data on all these things. So process the material properties without damage, then you go for the load increment. Then what you do is you first solve for displacement, the non-linear, because you have the non-linearity because of this damage. Then what you do is compute the stresses. Once you compute the stresses, from these stresses you go back and find the strain energy of the damaged ply or interface, and then you find out the damage indicator. So if the damage indicator is more than 1, then what you have to do is you have to reduce the load step. That means you have exceeded the damage indicator. So you cannot do that. So go back and reduce it. If not, then you update the damage indicator and go for the next loading. So in this non-linear thing, what is done is that we are just using the predictor corrector method. So at the k plus 1 load step, the residue vector is defined like this. So here your u is your displacement vector, r is your residue, then f is external load vector, and p is the incremental force vector or the nodal force vector. Then in the predictor step, using this truncated series, so this incremental load vector, load vector is defined like this. So you have the previous at the previous step plus this k into delta d. So where k is the stiffness matrix for the previous load step, and delta d is the increment in the displacement vector for corresponding external load increment. So this will give you, so if I go back and put this here, then I will get this. So this equation will give me this delta r residue, okay, as this. So this is your conventional incremental predictor step. So now in the corrector step, what is done is, now your displacement for the k plus 1 step is updated as uk, that is the displacement at the previous increment, plus the whatever displacement that you have got for the current load increment. So with this solution, once you have this solution, now you can obtain the stresses. Once you have the stresses, then internal forces are obtained. So in this thing, okay, when you are obtaining the stresses, so there is one more step, that is you have to update your damage indicators. For damage indicators are updated when when you are going from when you are updating your displacement for k to k plus 1 step. So you will, that way you will get this internal forces, then you update your residue, okay, which is not 0. So then you apply the corrector step, and this corrector step is given like this. So this is the corrector displacement. So it is given in terms of the current stiffness. So now here from the previous step to this step, now you have updated your damage indicators, okay. So with this thing, now you will get the corrected displacement. So in this entire process, so you have to assure that when you are starting from the step and to the end here, okay, the damage indicator, whatever you started and what you are at the end of the step, okay, it should be same. The reason is, sorry, okay, then once you get this thing, so you will stop when you reach the tolerance. So here, as I said, you should ensure that whatever damage indicator you started in that particular step, it should be the same when you are talking about this corrector 1 is the same, because the normal stresses sigma xx, yy and zz, they may do the reversal of the signs, that is compression will become tensile, tensile may become compression or so on, okay. At each of the step, you have to take care that we do not want this damage to increase during the compression. As we said that it should remain dormant in local compression. It should grow only when the tensile, the region becomes the tensile, okay. So otherwise it should remain dormant. So if that region is tensile, then you have to go back and look at the damage indicator if other corresponding thermodynamic forces, and depending on them, if your damage indicator is more than the previous one, then only you are incrementing or you are updating your damage indicator. So otherwise you will go with whatever is there in the previous step. So because of this frequent reversal of this local tension compression, you have to make ensure that these damage indicators or these regions are same in your load increment. So this is what it is depicted, in this figure. Okay, so now I represent some key results. So I'm not giving the details of this material, so I will just say there's a material this, okay. So this is classified material, so that's why I'm not giving the details. So I'm going to talk about some key results. So this is a 0-0 laminate, a very simple laminate has been taken. And this is the growth of the fiber breakage. So in this, we have considered a laminate with a hole, and the load is applied along this axial direction. So this is the evolution of the damage failure, sorry, of the fiber failure. So it starts at this location of the this hole, and as your load progresses, you see that this fiber failure is only is in this limited region. Okay, so we have not gone to the level that a complete failure of this plate. So this is the matrix cracking in the 0-0 laminate bottom layer. So in this case, the matrix cracking can also take place, and again, as you can see here, it starts in the region where you have the stress concentration. As you know that if you are applying the load along this direction, then you will have more stress concentration here and here. So in this case, this matrix cracking takes place here, and it grows like this. So as you can see here, this it is along the length of the fiber. Okay, so this is the preferred direction, okay, of this matrix cracking. So I'm not sure if you are able to see it. This is at one level. There is some other region, okay, which is at slightly lower region. Okay, that means the intensity of the damage is slightly lower. So also you can see that it is propagating here, then at some stage or towards the end, it also starts from the edges, because now your material has degraded and it is showing its effect at the edges also. Then this is fiber matrix debonding in the 0-0 laminate again, and the bottom ply. Again, similar results, you can see it starts here, okay, and then it propagates along the fiber length. Then this is delamination in the 0-0 laminate. So in this case, I think you are not able to see it, but the level of the delamination that you see is very small. So it is not actually delamination, but it is, you should interpret it is that the interface between the these two plies is weakened. Okay, this is not a complete delamination in this case. Okay, because what we are doing is that we are just reducing the stiffness of the interface. So this is another laminate. This is plus minus 45 laminate, and what is shown here is the matrix cracking. So again, the matrix crack starts from this edge of the hole, and as you can see here, it is going in this direction and this direction. So this is nothing but your plus minus 45 fiber direction. So you see that the cracks, matrix cracks grows along the fiber line. So this is the preferred orientation of this matrix cracking. So it goes, okay, at certain stage, now it starts also from the edges, and then there is a cracking. So as you can see here, you have this plies plus minus 45, and the load is applied. So it is, load is applied off axial. So it is understood that the matrix will fail first, yes, because the fibers are at some angle, they are not oriented along the loading direction. Okay, so the more load, or the matrix is supposed to take the load. So that is why you see that the matrix cracking happening along these preferred orientations. So this is again the matrix cracking. So again here, similar thing you can see here in this case. So I think the previous one in the different mode, the shear mode, I guess, and this one was the normal, normal to the ply, fiber direction. Sorry. So again, in this case also you see a delamination. So again, what is happening? So you have the plies like this, plus 45, minus 45, and my load is applied like this. So why do you see delamination? Is that when you are applying the load, this plies will try to orient along the loading direction. So that will weaken the interface. Okay, so conclusion are just qualitative. So we have done this material non-linearity due to damage. Then here the prominent modes like fiber breakage, matrix cracking, fiber matrix debonding and delaminations are modeled and implemented, and the results presented are here according to our expectations. In fact, we have some experimental verification as well, but I'm not supposed to disclose that. So that's why I have not given. So with this, I would like to take you. Thank you.